Oh, nice.
Sure. So I already delegated me something.
Okay.
Tell the working group.
Okay. What do we got?
Is that feedback or candidates is not there. He's doing some serious stuff. Yeah. So if anybody asks me, then just tell them.
You can never truly be free of it.
Do you want that time in TSVWG? We got plenty.
You know what?
You want that time in TSVWG for the steward session?
Yeah, if you can. I think it'd be
What do
good
you
to
want, 10 minutes?
Yeah. It should be fast. I think we said 5 to 10.
Okay. I'll
It
probably,
just seems like it groups slow with the other stuff.
yeah.
If we have extra time at the end here, I don't mind coming into it here, but like, all it does is.
Well, you're doing it, right?
We can't. No, it's Switzerland.
Oh, remotely.
Yeah.
Yeah. Does he want to? Okay. We could do them both places. I don't care. But like, L4S really is there.
Like the conversation is there, so here would just be a teaser for Wednesday. Go attend there if you care.
Yeah, you can have 10 minutes.
If it's basically we have 10 minutes at the end, we'll do that. So
All right.
that's fine. But either way, we should do it in TSV.
Yeah. Okay. Sounds good.
Thank you.
You got it.
Yeah, if you don't mind responding to the Fed just so he knows what time he needs to wake up, that would be cool.
Yeah.
Cool.
Thank you. We're going to get started in about 2 minutes, so good time to find some chairs.
Stewart in section 1, and Mohan's going to move to section 2.
All right, let's get started. Welcome to the CCWG session at IETF 123. We're here in Madrid. A few quick notes: this session is being recorded. Please make sure that you scan the QR code in the back of the room or go find the link in the agenda on the data tracker to join the Meet Echo session. You will need that to be able to enter the queue when you wish to speak. You can also see the slides, participate in the chat, and it also helps us keep track of who's here and how large of a room we need for next time. It is Monday, so please make sure that you extra read the note well. These are the terms under which we participate in the IETF. Please take extra good note of the IP declaration policies, as well as the guidelines and code of conduct. If you see any code of conduct violations, please report them either to the chairs, the AD, or the Ombuds team. We've got some helpful links if you're looking at a PDF version of the slides. And we've got a nice agenda today. So we're gonna start by asking for someone to take some notes. Can we select a scribe, please? Martin, thank you so much. All right, and with that, unless anyone would like to quickly bash the agenda, we've got a potential additional as time permits talk at the end from Stuart, which will be a nice preview of some upcoming work on Wednesday. We'll see where that goes. So starting us off, we've got a hackathon update. I have a clicker here. Give that, and give it 1 second.
You can start, I guess.
All right, test the clicker, make sure it's working. Beautiful.
Yeah, I think it is. Yeah, hello everyone. I'm Mohit, and we actually set up a hackathon table this time as well for testing congestion control and queue management algorithms. A lot of students participated. About 5 of them are remote and 5 of them are right here. So they were with me and we worked over last 2 days on achieving some of the objectives. I'll go through these objectives quickly, and then I'll also have a couple of slides to tell where we plan to move forward and where we are looking for some inputs from the community to understand how we can do the most useful thing in terms of building the tools. So the objectives for this time's hackathon were 5. First one was testing FQCodal and FQPy using different tools, NS3, Nest, and Wi-Fi access points. We did not bring Wi-Fi access points here for the hackathon because the travel was quite long and a lot of intermediate hops were there. But we did use NS3 and Nest, and then continued forward the testing. I'll explain what is that we tested. We were able to complete this objective. Particularly, I was working in the hackathon on the first objective. Another 5 students who were remote were working on the second objective, which was about something we found as a problem with Codel, and we wanted to fix it. We actually worked on it, and yesterday we made a presentation about it at Hot RFC as to what was the fix and how did we manage to get it done. The third one is still pending. We look forward to completing before the IETF. We could not do it during the hackathon, which is about the draft that will be presented after this update of hackathon. Our author Michael will be presenting that update, and we wanted to just have an NS3 example for people to play around what happens with the update in the draft and what happens without the update in the draft. And then we also had a partial implementation of RFC 8511, alternative backoff with ECN, which was pending from long time. So we decided to wrap it up during this hackathon, and we managed to complete it by opening the merge request, and the NS3 community is already actively reviewing it. We already got feedback, and we were having this exchanges going on. And the last one was about other 2 students here who are working on the implementation of hierarchical token bucket queue discipline in NS3. we managed to do some testing and validation of that, but still it's pending. So that's why I said it's partially completed. So we used CCPerf like last time, but this time we actually added more tests. So we tested with all the green color things that are available on the left, which is steady state and transient state. We had total 5 tests performed this time. The ones which are highlighted in blue, and actually the ones that I have colored in green are also supposed to be in blue otherwise. Those are the ones that are available by default in CCPerf, and more importantly, they are compliant with RFC 9743, which is CCWG's work, which explains what are the tests to be done if you are proposing a new congestion control algorithm. So we use the same tool and we continued our testing. Found some really interesting results. I just briefed about it in yesterday's hackathon update. I'll talk more about it in the Wednesday's TSVWG, where we found the sensitivity of the queue management algorithms to the fact when RTT is varied marginally, we are actually seeing a lot of disruption in throughput. You can see on the first graph on the left-hand side. So we'll talk more about it in TSVWG when we present the draft on FQPI. This is the merge request, which has been opened, and we have already been getting feedback from the NS3 community. There were lots of questions. We have been able to address it. Maybe before this IETF concludes, we should be able to complete getting this merged in NS3. We also generated some sample plots without alternative backup with ECN and with alternative backup with ECN, and these plots were also uploaded to the NS3 community to kind of help us validate it. So this work also got done. We are also launching by the end of this month officially the AQM evaluation suite in NS3. This suite was developed a few years ago, but it was not available on the NS3 App Store. This month and we'll have this suite available on NS3 App Store. This suite is compliant with RFC 7928. RFC 7928 is a characterization of the AQM guidelines. If you are proposing a new queue management algorithm, what are the set of tests that you should perform? There are at least 26 tests that have been mentioned in the RFC 7928. So what we have done is we have built a tool wherein actually you can come and specify which section of RFC you want to run. So if you look at the left-hand side one, if you say I want to run section 5.1.1, it actually is pointing out to the RFC 7928 section 5.1.1. And then you will actually automatically get the results for that specific scenario. We also have certain configuration options. You can either specify the section number, or you can specify the name of the RFC section, or if you want to run all 26 tests, just specify in English all, and then it will run all the 26 tests what are mentioned in RFC. So this tool has been built on top of NS3, and we are officially releasing it as a part of the NS3 App Store. There's also a discussion going on in the NS3 community whether this should go into the main line of NS3 or should it be a separate app. And some feedback from this community will also help us to tell the NS3 community. So NS3 community has asked me to seek feedback from IETF as to what they would prefer. Would it be easy for them if we put it in the App Store, or they would prefer it to be a part of the main line? So if anybody install NS3, they have this suite available with them. We are looking for collaborators. The roadmap for the next IETF from here onwards till November is that we also want to focus on building, like we have this AQM evaluation suite, we want to build congestion control evaluation suite as well. And for NS3, we have a good head start in terms of CCPerf, which is built by a German university. We'll take that and try to customize it and try to take it to the next level. But for Nest, which is based on the Linux kernel, because for example, during the hackathon, a few people came and said, we have the Linux implementation of the congestion control algorithm. It's not available in NS3. How can we test it in NS3? So you cannot test a Linux implementation in NS3 because you need to re-implement that algorithm in NS3, and that can take a lot of time. But if you have a Linux implementation, we can use Nest, which was presented in last CCWG meeting at Bangkok. And we are actually trying to build it from scratch. And we need help for these 4 bullets. We need to talk to the community to understand what are the well-established topologies. We of course know dumbbell is one, but is there any interest in multiple bottleneck topology also? Should we consider that? We also want to know what is the application mix that the community would want this tool to support by default. For example, large uploads, downloads, web traffic. Do you want dash traffic, HLS traffic, or any SIP flows? So what is the kind of configuration that we should put in the application? And more importantly, RFC 9743 has quite a lot of scenarios. So we want to go in phase wise and build one phase at a time. So we want to understand from the community which scenarios we should prioritize first in the first phase, so we can then actually have a timeline. And if there are any other points that you would want us to discuss and help us build this evaluation framework, we are looking forward to talking to you. So, yep, that was the update from our side. I'll be here for the IETF week and would be happy to discuss if there are any inputs on this. Thank you.
Hey, sorry, Lars Eggert, the tool doesn't let me get in the queue. I have a ancillary question to your presentation. So great work. And the last thing you said about Linux and not being able to do this in NS3 sort of triggered me a little bit. There was this summer of code thing called direct code execution for NS3, which for those of you who are not familiar, I think the idea is that you dynamically preload a shim library that intercepts all the system calls, and then you can run arbitrary binaries in NS3. Have you guys worked with this? Is this in any sort of shape available? Because I think that would be excellent for some of the quick testing everybody's doing.
Yeah, I think we had this discussion with you in Bangkok
Probably.
meeting. Yes. So we do work on direct code execution, but what we have gotten the feedback from our users is that they find it extremely difficult to set up DCE on their platforms.
Correct.
So we did not choose to go DCE way because we thought it will be making things further complicated rather than making it simple. Another challenge that we face is we have lack of maintainers in NS3 who can upgrade the Linux kernel version supported by DC. So for example, we support very old version of Linux right now. We have hardly 4.9.
Yep.
And 4.9 because somebody requested BBR implementation. So that's why we had bumped up at that point. But now we are already, Linux kernel is at 6.
Don't use the BBR in 4.9.
Sorry?
Don't use the BBR implementation
I know,
in 4.9.
but some people wanted to test it. So we had increased the kernel version. But now again, kernel is at 6 plus. We haven't gotten maintainers who can help us increase the version support.
Yeah, I don't have the maintainers either, but so if we could sort of square that circle somehow as a community, I think that would be super helpful for experimenting with these congestion control implementations.
Yeah,
thank you for the work you're doing.
Thank you.
Alessandro Ghedini, Cloudflare. So to echo what Lars said, we have, implementation of Quick that don't necessarily go through the Linux kernel, and it would be really, really helpful to be able to set up test environments that where we can use our own implementations. The other thing I wanted to mention, which actually we talked about during the hackathon for a bit, which is, there are all these tools where you can run tests, but for sort of transport protocol implementers, it becomes really hard to have to come up with test cases for every implementation. So having some common test vectors that we can use across implementation would be very useful, starting from the RFC, whatever that you mentioned.
Yeah.
But also having, maybe we can talk about this during the BBR session, but even having like congestion control algorithm specific test cases where you can maybe test the BBR startup phase and how you transition to other phases would be very helpful. As well as you mentioned NS3, having like a BBR model for NS3 where we can compare our own implementation to like a maybe like known good implementation would also be useful.
Yeah. Sure.
Roland Bliss, KIT. Did you look at the network simulation cradle? Does it work? Doesn't it work? So that would be
network simulation cradle is actually obsolete. DC is the new version, the one that Lars mentioned.
I'm not an NS3 expert, but at least the documentation says that it was ported to NS3.
No, it has been made obsolete now. It's quite old. The newer version was DC.
Okay, sorry.
Yeah.
All right, I think that takes us to the end of our queue. Thank you. I do want to highlight, there's two pieces I think coming out of this that are really key, especially for people in this room to help with, in addition to the set of bullets that we have here. That first one around kind of topology design. We have a long history of coming in somewhat later in the process saying, oh, but did you think about this particular case? And this is a particularly good place to help compile that list. And the other point is a really big thank you for a lot of this work. This energy and a lot of this work is part of what helps us have the ecosystem that enables us to do a lot of the design and work that we're doing in this working group. So thank you very much.
Thank you. Thank you, everyone. Thank you.
Michael. I have a clicker for you.
Okay, yeah, here's an update of our draft on increasing the congestion when the sender is rate limited. We did two very small things and one bigger thing, which was to try and address Martin's request. The small ones are just to be more precise about what we mean with RTT in one place, and in another place, well, there is an example of how things will play out. And that example talks about the initial window as the number 10. Well, it's okay as an example, but it's nicer to talk about initial C wind based on these RFCs. Now, the draft as it was, it had three rules in it, one with a must, one with a should, and one with a may. The idea, the main motivation of this work was to say that the specs as they stand, they allow a sender to unlimited, to increase the congestion window without any limit when the sender is rate limited, which is what most people don't actually implement. They implement something that just caps it when the sender is limited by the application or the receiver window, for example, which is also a bit too conservative. Because the congestion control rules would allow you to increase as per the rules based on what you've sent in the previous round trip. So what we did is we said you must limit it somehow, and then we said you should limit it with this rule that we think is reasonable, and then we have a may as well. And Martin rightfully complained that this is a too vague statement for something that is qualified as a must. So our approach to try and solve that is to remove the first rule and, well, change it as here, to go from three rules with a very vague must into to two rules where the not so conservative behavior that we prescribe, this limit max FS, which does allow you to increase further on the basis of what you've sent in the previous round trip, is written as a must because that only defines an upper limit anyway. Right, so it's the same as with the regular rules in 5681, where you have all kinds of congestion control rules, but it's always legal to send less than that, which is why we think that makes sense to qualify as a must, and the may stays the same. And, oh yeah, and then there was the point about pacing. The thing with pacing is that we believe we have a good statement there. I think we have an answer to any concern you may have, but people have brought it up again and again. So here's me quoting the text in the hope that you like it, or you tell me what exactly should change about it, because a concern has been raised without actually giving us anything concrete to adapt. What we say is that pacing mechanisms try to avoid the negative impacts coming from bursts, which is usually without limiting the number of packets that are sent per RTT. The thing is, if you do it, if you use the application, if the application asks pacing to pace at an even lower rate, then you're again being application limited, whether this is based on pacing or whatever other vehicle you enter in the other space, which is okay. Then we have that. So the limitation of max FS is measured over an RTT. If pacing applies within an RTT, then nothing will change. It's going to be the same logic. And if you use pacing as a vehicle to reduce your rate further, then the rules apply that in the next RTT you should be allowed to send more based on how the congestion control algorithm decides. And that is what I have. Comments?
Especially anything on that particular pacing paragraph, if you want to go back a slide. Go back a slide.
Okay, yeah.
Cool. Thumbs ups, thumbs down. Food coma from lunch.
So if everybody has been eating and is getting tired now, I think we should ask for working group last call.
I do think one of the questions is if we think we wrapped up enough, this is a good time to ask people to give it a full pass, right?
Yeah. I was kidding. So.
We can always do a poll as well.
Yay.
Oh, hi, Lars.
Lars Eggert Mozilla now managed to join the queue. So I'm lacking context to give you feedback on this, and I wonder if you can sort of, because it's been too long that I read the document, so I don't remember what Section 3 rules say. Is it the stuff we had before? So what does that paragraph intend to be saying? So I get that you want to have a max flight size, which says don't send more than this per RTT.
Yeah.
And then you say as long as the number is unaffected by pacing, which is the max FS, I guess.
Max FS is the maximum flight size that you've used up until now. And when you enter recovery, it's being reset, right? So you increase your window and you increase flight size, and the maximum flight size that you've ever used as you're in a phase that increases your window, be it slow start, congestion avoidance, whatever, what have you, that is the basis for deciding how much you can increase further in the next RTT.
Okay. So unrelated to the text on the slide. So as somebody who's been struggling with pacing a little bit in our implementation, right? So I'm kind of questioning how much whatever we write here at the application layer, especially if you think about quick, will actually be measurable in the network, even one hop deep into the network after packets have gone through the kernel and the NIC. So is this specificity on how you fine-tune pacing actually gonna do anything in the real world?
No, that's more or less the point here, to say that pacing doesn't make a difference for the logic of this algorithm.
Okay. Right, fair point.
That's what this paragraph is saying in short.
That's a very nice way to tell me to read the document.
It just doesn't make a difference. That's the...
Gory's up next.
Marwan Fade, Cloudflare. I'm glad Lars broke the ice, because I'll be honest, I think I still don't understand I think what the paragraph means to say is if the application wants to pace and it's less than the possible send rate, then you ignore it. It's just a confusing. I don't know what it means to say. That's my only concern.
Okay. Okay. We can rephrase it. The point is to say, well, okay, Gory, you wanna?
So Gory has as an individual. We're designing a camel, right? You need to read the whole of the section. This paragraph is the bit that we've tried to get right. The whole of the section needs to be read to understand why this paragraph is there and what it means. And it means basically, as Michael says, that this is not a problem. But you have to read the rest, because this is the bit we were asked to rephrase. And I'll let Ian comment, because Ian was the person who started this by asking a sensible question in another meeting.
Ian Sweat, Google. I will read the entire section to provide full feedback, and is the short answer. Thank you for adding something. I'm a little concerned about the statement. This is usually without limiting the number of packets that are sent per RTT. And the reason I said that is because for congestion controllers like BBR, the typical pacing rate is less than the C-wind, basically. The pacing rate times the RTT is less than C-wind. So
that's okay. I can take that sentence out. The point that we can take that sentence out. Okay. Usually, okay. The point is, if you don't reduce the rate below the congestion window, you're not being application limited or rate limited as it is, and then it doesn't make a difference for what we say here. And when you do, well, then this logic of this draft applies. So it doesn't really matter is the bottom line.
You're right.
We can rephrase that and take that sentence out, no problem.
Okay. I'll provide more detailed comment, but thanks.
Thank you.
Okay.
So this is a document that currently has no open issues, other than maybe a possible editorial rephrasing of this part. what are our next steps here? This seems like a particularly good time to ask folks to give the document a full read. It is surprisingly brief in the time commitment that would require. So I think this is a good moment, assuming the authors are all thumbs up on this plan. I think this is a good moment to say, hey, we think we've covered everything. Please give it a deep dive. Send comments to the list. Open issues on GitHub, however you prefer, so that we can make sure that we're ready to go. And then I think after that we start thinking about last call modulo. Martin.
Why don't we just do working group last call? That's like the signal
can do
for
that right
everyone to read it.
Sold?
I mean, maybe once this is done.
Yeah. Okay, so we do a little bit of editorial cleanup and then we start a last call. I'm seeing general nods of assent and enthusiasm. I might be adding the enthusiasm. All right. Cool. We will do that. And next up, I believe we have an Ian.
Hi, Ian Sweat from Google. Be talking about BBR update. Thank you. So we just published draft 03, and I'll go through some changes. A lot of the changes are really focused on making the draft easier to read and making it less TCP centric. Now that those two projects are done, but I do think it's moving in a much better direction. So this is, an outline. This largely kind of follow the same format as before. Go over some updates, summarize some open issues. At least a few of the issues are the same issues that were open before because we still need experimental data. So, I realize that not everyone can provide that, but for those who can, any help is definitely appreciated. Adopted in October 2024. Here's how you collaborate. And yeah, nothing really changed here. So, right. We documented our stance on ECN. We discussed this at the last IETF, I believe. And so we did not prescribe a specific response, but we do say that if you negotiate ECN, you must treat CE marks as congestion. So ECN is one of the reasons why the BBR draft is experimental. Martin kindly pointed out that there was no explanation as to why. There are also some various issues with kind of rate sampling that are not exactly perfect, particularly under things like application limited behavior, interestingly enough. There's a little bit of reorg. When the drafts got, the delivery rate sampling draft got merged in with the BBR draft, which I think happened right around the time it was pulled into the working group. It was sort of shoved together. It turns out that put all the delivery rate section like 4 levels deep in the draft. It was kind of difficult to find actually, if you look at the table of contents. So we just kind of reorganized it a little bit. And we're trying to use in-flight more precisely and consistently. Previously, we used bytes in flight and packets in flight and in-dash flight and all the variations that you might think. And a number of other editorial changes. So this is something from before. There's still 2 open PRs where we were hoping for some experimental data. One is to propose to change the BBR drain to the experimentally derived version. And the other one is to remove the ACK phase from the pseudocode to simplify it. There's a question as to whether it's exactly identical with the simplification or not. I think it's not exactly identical, but in practice, we think it likely is. But I think we only have one implementation from the real world. So another implementation would be helpful to validate that in practice this works properly. One issue came up recently, which is how do you define when you're sort of coming out of idle? And there's this idea of unacknowledged and rather than in flight, and it's a subtle difference. But the key idea is if, at least for TCP, if there's, send next and send UNA are equal, like you can't have bytes in flight that will be in the future acknowledged no matter what. Like no matter where that packet got stuck in a buffer in the network, it has already been acknowledged. You have no outstanding data. For transports like Quick, in-flight could be 0, but you could have spuriously declared packets as lost, and then they could end up being ACKed at some point in the future. And when you're restarting from idle, you kind of reset the timestamp of when you start the bandwidth measurement to kind of now. But if there are packets that are actually in flight that could be acknowledged in the future, this could cause you to overestimate the delivery rate in the bandwidth estimator. So it's kind of a subtle issue. If people have thoughts on good solutions for this, please comment on the issue. I think Joseph and I both suggested a kind of a high-level concept of a fix, but neither of us have a PR for it. It is rather trivial in TCP, which is convenient, but yeah, for non-TCP transports, it's potentially a problem. So we're still working on text to kind of fix the pacing spec, actually in the application limited section, appropriately enough. And we got some good feedback from Christian. The text that is currently in the PR is kind of below. I'm not going to read through it, but the issue before was that the current text was kind of not quite generic enough. Again, it was kind of TCP/implementation specific. So, suggestions welcome. Text around these sort of things is quite difficult to get right. So, as long as the key concepts are covered, that's certainly helpful. We continue work on generalizations in non-TCP transports. So 2 of them are there, which is bandwidth estimation still uses sequence number, SEQ names. And there's a few other sections that are very TCP centric. So. Another issue in terms of a design issue is that probe RTT and whether it should be every 5 seconds or 10 seconds. It was initially 10 seconds. And then when the probe RTT was changed to be less deep, like it only drained half the pipe instead of going down to basically like 4 packets, it was shortened to 5 seconds under the theory that you can afford to do it twice as often if you're draining half as much, was kind of the theory. But there's actually a fair amount of experience with the 10-second number, including in the move fast BBR implementation. And there's kind of a high-level rationale that 10 seconds might actually be better for real-world applications because things like ABR, things like Dash and other video streaming very well might always go idle at least once every 10 seconds. And if you go idle often enough for more than I think 2 RTTs, BBR will just skip probe RTT entirely. And probe RTT is admittedly known to be kind of a bit of a gotcha in terms of consistent performance. Yeah. Actually, in this case, I think we think that the experimental data we have validates that moving to 10 seconds is a good change. I think in this case, what we would like is simulation data, not experimental data. I think we're fine on experimental data. So this is kind of this is the opposite of what we usually ask for. So if anyone has a good simulation environment that they like and want to try out this change in that environment, that would be greatly appreciated. Oh, Christian, sorry.
Good morning. Yeah, Jan, on this business of probe RTT, there is a specific condition in which probe RTT matters, which is competition. BBR, in a sense, is a delay-based algorithm because the delay is basically the part of the divider between the byte in flights and the delay there. And as such, it has some latecomer advantage issues. I mean, limited, but there are some. And the probe RTT is particularly useful when you detect competition. That is, if you detect competition, going into probe RTT will ensure that people competing have the same view of the RTT. So I wonder whether it should be really delay specific, like every 10 seconds, no matter what, or whether there should be some kind of a test that says, I feel that the network is really hot. I may want to do something like that to stabilize the competition.
I'm not sure if Neil's on, but oh, actually, let me clear the queue and then. Oh yeah, Neil is on. Okay.
Yeah, this is Neil Cardwell, Google. Yeah, Christian, I think that that makes sense, and I think that is a great direction to investigate. And in fact, I mean, most delay-based algorithms kind of implicitly do that in the sense that when they sense excess delay, they pull down their C-wind. And so I agree that is a sensible direction to investigate. I think it's just that it's a whole research project of itself because once you're adaptively deciding to slow down when the RTT gets higher, then that puts you in a regime where it's easy to get fooled by delay signals from Wi-Fi and cellular links and other links where you can get a delay signal when the link is not actually building an excess queue. But I agree, it's a great research direction. Yeah, that's my sense.
Yeah. Otherwise, I think that 10 seconds is great. I mean, if what you want is some kind of a safety belt that lets you reset the delay in case you have no, then 10 seconds is better than 5 because this periodic slowdown is a pain in real-time conditions.
So actually, I like this idea. I was going to stand up and say the one thing I really don't want to say, which is, how does this work if we're just, in light of things like Starlink doing reconfigurations every 15 seconds, on the 10-second boundaries, you would miss some substantial changes. Maybe they matter, maybe they don't. And so it seems to me this idea of trying to be a little bit smarter might actually be worth investigating.
Yeah, the Starlink thing is a very good point. I think anecdotally,
I didn't want to say it, right?
Yeah, no, it's a very good point. I mean, and I think, and then maybe there is room for, a 10-second, or if for some reason something tells you that the path meaningfully changed, right? I mean, it could be, flow label, it could be something, I mean, yeah. So I think that's an interesting addition, and probably we should file an issue for that, because I think there certainly are cases when you actually know, like, I am taking a substantially different path now, and I really should do something about that and readjust.
Martin, all right, does Neil have more?
Nothing to add. I mean, I agree with both of the suggestions. Yeah.
All right, Martin Duke, Google. I hear what Neil's saying about this being maybe a big research project, and what I suggest is maybe just add this to the experiment, part of the experimental. Just say, like, we have some problems with probe RTT, and we're lacking simulation data, as you said. We're lacking proof that it works in theory, even though it works in practice, and that there's other considerations, and that maybe one thing that we are uncertain on in this design is how this, and whether we should have some sort of non-numerical condition versus a fixed probe interval, et cetera.
Sure. Corey, I think you physically raised your hand.
Sorry, because I have 3 windows open in 3 different meetings, I didn't know which one to click. I kind of feel slightly uneasy about 10 seconds when you do have a RTT information that might tell you that that's really wrong. So I think it's worth a quick run around to see if we can have a, like, hey, it's good to do it in 5 type check that's not too impactful normally, but it would trigger if something went really different. I'm thinking about these strange Starlink ones, for instance, but there are other places where there are path changes, and it would be really nice if we had a little bit of information to go, oh, we'll be slightly more careful to do a check sooner. I don't think it would hurt the performance of BBR in most of the cases anyway, so it may not be a dangerous thing just to add in the spec and then say, well, we might take it out in future.
Okay, yeah, that makes sense. This is a naive question. Are there standard indications that the path changed that are like written down somewhere? I mean, I threw out flow label as an example because I know in some cases V6 flow label will subtly change your path, though sometimes not meaningfully. But I mean, I know sometimes there's OS level signals, I think, but
there are OS level signals in some OSs, and there are things like DLEP, etc., which signal back from your router that there's something happening upstream. They're all a little bit odd, and you also know something about when you're using a tunnel to get somewhere, and that tunnel does things. Yeah. For this, probably you see consistently min-RTT samples, which are much higher than you thought or whatever. I mean, reacting one way is more important than the other, so maybe you have a little bit of indication from the RTT estimator for this particular thing. I'm thinking on the fly, shouldn't be designing here, so we're going to sit down.
Okay.
Eric Kinnear as an individual. Yeah, I was actually going to add, so different OSs have different signals that things have changed. And I know we haven't necessarily even plumbed all this through, but it would be nice to have some provision for, hey, I have some external knowledge that this happened, is maybe a nice catch-all. Because, for example, say your cellular modem has switched radio access technologies. That's something that's often quite transparent today, but you might have gone from a wildly different condition, and you don't even necessarily have to be reconfiguring satellite accesses to have this happen. You could just be driving down the road or have launched some other app and something happens. So
yeah, the 5G to 4G switch is pretty brutal, for example.
Yeah, and like, there's a lot of places where, like, if we knew, hey, the world is different now, please go figure out the world you are now living in. That might be quite helpful.
Okay. Okay, I just want to make sure it wasn't like an RFC or some like BCP I should. Okay. Okay. I'm happy we could solve that.
Yep. Yeah, sorry, it's on here too.
Yeah, Joseph, go for it.
So I just wanted to comment about the part about being able to react to changes in the link. This doesn't actually check that because we're not changing the min-RTT filter length. We're only changing the frequency of probing. So if we have a bad min-RTT, probing every 5 seconds or 10 seconds doesn't change that much. We're still going to be stuck with a lower RTT for the whole period of 10 seconds. So I think I just wanted to highlight that changing this does not necessarily give us lower RTT estimates or does not reset the RTT estimate every 5 or 10 seconds. That already happens every 10 seconds only.
Thank you. Thank you for reminding me of that, Joseph. Neil, did you have one final thing to add?
Yeah, I just wanted to mention that, just a reminder though, that this stuff is very tricky because, so for example, if the decision to enter probe RTT becomes adaptive, then we've greatly increased the odds that some flows enter probe RTT and some don't, which means we've greatly increased the odds that some flows are leaving a backlog of packets in the bottleneck queue, which means we've greatly increased the odds that the min-RTT measurements made by anybody in probe RTT mode will actually overestimate the min-RTT, which means that we've greatly increased the odds that we may enter a sort of feedback loop of overestimated min-RTT and too much data in flight. So it's all, that's all just to say that this stuff is a little bit complicated and subtle, and I think it's a great thing to add, notes in the experiment section, but we probably shouldn't plan on making a change like this in the scope of the edits of the algorithm in the draft.
Thanks, Neil. Thanks for the reminder. I will move on. Some other open issues. The pacing issue we already talked about, and the application limited kind of text. Hopefully that is fairly close to done. A new issue Martin Seaton raised very recently was what is the BBR offload budget for Quick? Because it only talks about TCP. I think we don't have a clear answer to that one yet, but if you have strong opinions, please let us know. It certainly seems like it might depend on the implementation. There are a number of editorial issues that got opened, again, many by Barton Seaman. Definition of variables and some clarity around that, some language clarification, the units. So we talked about units last time. We are trying to move over to using bytes whenever we need to specify unit packets or bytes. That change is not completely done. And then finally, some pseudocode cleanup, so. And I think that's it. Yep. So thanks to all who've read it and filed issues. I think we're making fairly rapid progress in terms of editorial issues and minor design issues. Obviously, we have some larger design issues that we would like to get sorted one way or the other in the not so distant future. Yeah, any other thoughts, questions?
What's the roadmap look like for those bigger issues?
For the design issues, the roadmap?
Yeah.
I mean, I think really they should be resolvable in, by the next meeting if we really wanted to. I mean, I think my view tends to be that if we want to get this document largely done by the end of the year, we could, with the caveat that we are going to, have an experimental section that solidly declares a number of things that are not currently in production as experimental.
Gotcha, thank you. Lars, are you getting in the queue or not? Nope. All right, we'll just spot you while you do. All right, any other comments on BBR v3?
Right. Thank you very much.
Wonderful. Thank you, Ian. All right, next up we have Roland. We had some folks for some of the HPCC stuff, unfortunately could not make it today, so we took them out of our agenda and they will be here at the next meeting.
Hi.
Let me get you some slides.
I'm Roland. Yeah, okay, this is a short presentation about our paper that we had at Networking 2025. So this is joint work with Lucas and Martina. So we looked a little bit at the BUR performance of version 3 and also tried to find out what's going on. So without explaining how BBR version 3 works, actually, we did experimental evaluation. So no simulation, but real hardware, also no virtualization. We varied the bottleneck data rates between 100 megabits per second up to 10 gigabits per second. And we also traced the BBR internal variables in order to find out some root causes for the behavior that we've seen. Basically, in the paper, we looked at 3 different things. One is the self-induced queuing delay, and also the behavior with respect to delay jitter, and also how short flows using real-world traffic will behave. And this talk covers mainly the first and the third item. And for the second, you can see the paper, but I will talk about that in the conclusion as well. So the testbed looked like this. It was a Linux-based testbed with, as I said, the different speeds that we could vary at the bottleneck link. And we also use different buffer sizes, small in that sense, 0.8 BDP, 1 BDP, 2 BDP, up to 8 BDP. The experiments use the current BBR version 3 implementation. we had runs of 60 seconds duration and did 30 repetitions. We also induced artificial delay. So on the way back, this is typically a little bit better with respect to the performance behavior, since you don't have so many data that's queued up. So if you only queue up the X, and we did the measurements actually at the bottleneck router, which is here, the software-based router in the middle. And we also looked at the connection parameters at the end systems that are at the center side. So now we are talking about self-induced queuing delay, especially when the traffic is not limited by the application. So we have application unlimited senders. So for single flow, we looked at the self-induced queuing delay, and you can see here that we have the queuing delay for a setup where it's the bottleneck is 100 megabits per second, the RTT min is 50 milliseconds, and we have a large buffer. And the vertical magenta lines are basically showing either probe bandwidth up or probe refill phases. And what we found is that the queuing delay is it's relative here, but it's basically quite beyond what VBR version 1 actually did. And so that would be here at 0.25, while you can see that we are more in the range of 0.9. The explanation that we found is that basically we have 3 rounds or 3 RTTs where the estimated bandwidth is increased by the pacing gain of 1.25, and this inevitably leads then to larger queuing delay. And the self-induced queuing delay also prolongs the round trip times. So BBR version 3 creates actually higher peaks. That was at least unexpected by us. So that is noteworthy, we found. So second thing we saw is that self-induced queuing delay may also come from phases before that probe up phase in the cruise phase. So this is a result where you can see the BBR's estimate in the lower part of the plot, the bandwidth estimate, and in the upper part you see the queuing delay that we measured at bottleneck. And you see that the queuing delay actually ramps up before the probe bandwidth up phase. So setting is the same bandwidth-wise and RTT-wise. And we found that this is caused by bandwidth overestimation due to natural jitter that you have in the systems. So the measurement noise in the delivery rate samples cause this behavior. So as I said, the queuing delay even increases before the probe up phase. And you can also see that the bandwidth estimate is beyond what's actually available, indicated by the red horizontal line here in the lower part of the plot. So we're still at a single flow, and what we found is it gets worse at higher speeds and small RTT min values, actually. So this is a CDF over the samples we took. So these results here are at 100 megabits per second, so this doesn't seem to be so bad, but when you look at 500 megabit per second at bottleneck rate, then you see that it also varies with the RTT and gets worse. The RTT gets lower, so CDF is much broader in that sense. That it starts the queuing delay, it starts to ramp up the queuing delay much earlier. What about 2 flows now? So we also looked at 2 flows at different speeds, different RTTs, and also different buffer sizes, which are next to each other here. And you can see that for the small buffers, of 0.8 and 1 BDP, there are cases where BBR even creates packet loss because it exceeds that buffer capacity. For the larger buffers, you can see that the queuing delay is around 1 RTT min for more than 50% of the time for the larger buffers. But it actually is able in the 8 BDP buffer to limit that let's say around 2 RDT min. The cause for that is present since BBR version 1, because when the flows measure, they overestimate the available bandwidth altogether. So in sum, and then they are sending faster than what the bottleneck actually provides as capacity. If you increase the number of flows, there's a small tendency that this gets a little bit worse, but it's not really concerning in that sense. So here we have varied the number of flows to 4, 8, 16, and 32 flows. And also varied the bottleneck speeds, as you can see from left to right, and also the RTT. And as you see, for the larger speeds, the limitation around 2 RTT min works quite well, while for the lower speed and the lower RTTs, we have actually some exceptions. And we found that this was caused by the extra and offload budget mechanisms in BBR, because they increase the congestion window in relation to what's in flight, and that's at these lower RTTs and lower bandwidth than quite a bit in that sense. So much for application unlimited flows. So what about short application limited flows? This is just a single plot showing short flows from a real world trace. What we did was taking a 50-minute Mavi trace and replay that. That was recorded at a 10 gigabit per second link and replayed that at 3 gigabits per second. So we actually extracted flow characteristics and started senders that actually were able to replay the flows at this speed then. And what you can see here in the CDFs of, so on the left we have BBR version 3, on the right we have Cubic, and you can see that in the CDF that we also varied the, we varied the RTTs, and we had different replay models. But anyway, you see that there's a trend that BBR is actually increasing, or the CDF of BBR flows is increasing between 1 and 2 RTT min. So this is also a large buffer up to 8 BDP. And basically, if you compare it to Cubic on the right-hand side, then you see that Cubic is much more evenly distributed, while here BBR version 3 is able to limit the let's say queuing for the debuffer up to 2 RDT min, which is nice. So okay, yeah. To wrap up, we also confirmed other known fairness issues of BBR. So RTT fairness is inherent with the scheme because large RTT min flows prevail due to the congestion window limit based on the BDP. Sometimes we also found unfairness to Cubic, but that depends on the particular setting, the buffer size, and so on. Well, this is all well known. We also saw sometimes long convergence to fairness. And with respect to the self-induced queuing delay, BBR creates self-inflicted queuing delay around 1 RTT min for a single BBR flow in our settings, and more than 1 RTT min for more than 50% of the time for multiple flows. So if you compare it with the old BDP rule from Cubic, that's not much of a gain in that sense. But yeah, for delay jitter, there's a good message actually that there was a paper claiming at SICOM, I don't remember, was it 22 or 23, that said, yeah, BBR will, as delay-based congestion control, will be sensitive to jitter and actually, yeah, be preempted. Or having problems. So flows that are affected by jitter will lose their bandwidth share. We found out that this isn't the case. At least it's a little bit influenced, but it's not starving, what the paper was claiming actually. And then short flows, we found that it actually slightly improved. So we used the slowdown metric as well in order to measure what's happening in the performance. And we found that the slowdown values were a little bit smaller, which is better for BBR than for Cubic. all the shortlist flows. And we found that, yeah, basically the reason for that is BBR avoids completely filling the deep buffers, but as I said, it at least to some extent fills up the buffers. And that basically concludes my talk. Thanks. Questions?
Questions, comments? Ian.
One quick suggestion is that I suspect the delayed jitter results might be much better in your tests because of the extra act window that was added to BBR at some point. But so if they picked up code from, say, 3 years ago, that probably wouldn't have been in there. And the more recent code definitely has it. So that's a possible explanation.
Yeah, okay. Maybe the case, but I also remember Neil actually replying to that, let's say, paper saying, oh, I think you didn't model BBR correctly in that way. And that was also my feeling, that I didn't see how the model that they applied to the BBR was reflecting what BBR is actually doing. So in that sense, maybe a conceptual thing, maybe also some kind of detail, we don't know, but yeah, I think the actual model that they applied in the paper isn't really matching what BBR is doing. That was my impression, but maybe I'm wrong.
The extra act, basically the Wi-Fi aggregation patch, as Neil has sometimes previously referred to it.
Christians in the queue.
I was struggling with my mouse to click on, sorry. Just a question. In your simulation, did you do simulation of extreme Wi-Fi jitter?
No, actually, it was not a simulation, it was a real test bed, and we introduced the jitter artificially. We actually did use two different jitter schemes. So one was more or less completely random, while the other one was more like a bursty jitter, but we actually didn't model something like real Wi-Fi jitter or so. That we didn't do that. So for details, please look into the paper that's described there.
Yeah, that's a general question for pretty much every evaluation of congestion control. I mean, Wi-Fi works very well most of the time. There is one Wi-Fi scenario in which we see some extreme jitter. I suspect it's because it's a misconfigured Wi-Fi network where you have several networks in the same neighborhood that are hitting on the same Wi-Fi channels. And that creates an issue like the hidden receiver problem and things like that, which Wi-Fi reacts to by effectively doing a layer 2 retransmission, and those can create significant jitter. We see the normal delay being like 4 milliseconds increasing to 250 in some cases.
Yeah, okay.
And so as a general comment, it'd be nice if in further simulation we could evaluate this kind of thing, because it's a really nasty environment.
Yeah, okay. As I said, I mean, we tried to provide a very general model, and one that is actually behaving a little bit like batching up the packets behind some kind of packet that's waiting for, let's say, access to the channel. So this might be similar to what Wi-Fi is doing sometimes, but maybe not. So yeah, it would be a good idea maybe to have more precise models on that.
The problem with Wi-Fi is that they are doing exponential backoff. They are doing exponential backoff, and exponential backoff can exponentially increase the jitter.
Yep, yep.
That's yeah. Okay, but that's a nice paper. So thank you.
All right, Neil.
Yeah, hi. Yeah, thanks for doing this research and reporting these results. Yeah, I think one relevant aspect of VBR v3 here is that the decision in that particular version to allow higher queuing delays was kind of related to a set of trade-offs, mainly or partly motivated by some issues we saw with earlier versions of BBR with Wi-Fi links and high-speed data center links, like 100 gigabit or 200 gigabit links. And some of the dynamics that we see there that are kind of tricky are that with those environments, the min RTT can be much, much lower than the typical RTT just because of the link technology. So kind of along the lines of what Christian was just saying, you know, often a typical Wi-Fi link might have in a house or an enterprise setting might have a min RTT of, you know, say 4 milliseconds, but the typical RTT might be 20 or 40 milliseconds, you know, like an order of magnitude bigger. And in such cases, and sort of analogous issues with data center RTTs as well. And so, because of that, you know, that was kind of one of the main motivations for having the bandwidth probing last more, you know, at least one packet times round trip, and then, you know, the decision to go longer is a sort of separate and but related decision. But anyway, I wanted to just mention the sort of motivation there and suggest that, you know, if folks want to do research following up on this, other things to look at would be, you know, investigating dynamics on real Wi-Fi links and real high-speed data center links, because the motivation for some of those features might become more clear. But thank you very much.
Yeah, thanks for the comment. I guess it would be good to document that actually in the draft also. so giving some design backgrounds if there are these kinds of trade-offs. So I'm not sure whether they're already there. So I've actually to reread the latest draft version and maybe also we'll comment on that.
Very nice. All right, thank you very much.
Thank you.
All right, as I mentioned earlier, some of the HPCC folks are not around this meeting. They'll be here next meeting. I did have a question for some of our BBR authors, which is, what do we think our next steps are? Because we've talked a lot about different things we want to experiment with. We've talked about gathering data from the real world. We've talked about gathering simulation data. We've been making some really good progress getting through a bunch of issues. Thank you very much for all the text updates.
My personal perspective is getting experimental data from the two things we mentioned last time as well as this time, and getting kind of a resolution to the 5-second, 10-second probe RTT issue is probably, in terms of actual design questions, those are probably the big ones. And they're not even really that big. It's just like, we need data. I think there's probably at least another 3 months of editorial fix-ups that we need to do no matter what, whether it's addressing questions like the motivation for the extra ACT filter or just kind of like finishing the process of TCPing the draft, whatever you want to call that. So I don't know, is that helpful or do you do?
Quite helpful.
Okay.
Yeah, I think as we get through that next cycle, essentially, I think we want to start people thinking about what is the next phase of, do we go test a bunch? Do we deploy a bunch? I know we asked about people with other implementations. If there's folks in the room here or on the list who have some of those implementations, I know people were talking before. If anybody has any updates in that area, I think we're kind of looking for what is our comfort level with the current design. How are we going to then go apply a lot of our different experiments against it, and make sure that it does all the things we said we needed to make sure it does, etc.
Yeah. How many implementations is a good one? I mean, obviously there are 3 that are kind of listed kind of in these slides and stuff, but I know there are others, possibly Alessandra's.
Yeah, you've got an Alessandra right behind you.
It seems like it seems like 3 or 4 is probably enough for an
Pretty good.
experimental draft. Okay,
Yep.
as long as they're actually deployed, which they all are. So.
Yeah.
Yeah, Alessandro Ghedini, Cloudflare. So we're working on a BBRv3 implementation for our quick stack. A lot of the issues that we are running into that I mentioned before is testing that the implementation is actually correct. So I don't think it necessarily needs to block the draft, but it'd be useful if, I don't know, we spend time on maybe defining some like test scenarios for specifically BBR, where you say, you know, this happens and then this is how the congestion control reacts, and then you can verify, okay, I'm implementing this correctly. Because I don't know, maybe some of the people that have, you know, some of the longer running BBR implementations already went through this and they have their own test suite, but for all the people that are coming to this now, it's sort of a lot of work, and we don't necessarily have all the experience in actually working on BBR. So part of that could be, you know, the tools that Mohit presented, but we would also appreciate like some input from like more experienced, you know, developers that already deployed the algorithm. Another sort of issue that we've had is it's kind of hard to implement BBR just looking at the draft. It might be, I don't know, are we holding the draft wrong? If other people have similar issues, maybe we could spend time on writing down some like implementation guidance, maybe. Again, like it doesn't necessarily need to block the draft, but there are all these cases that maybe Google already ran into, or Meta, that could be useful for other people to also understand, so that when we actually deploy things to production, then, okay, maybe this is what we're seeing is because of this thing that they already fixed before. So I don't know how useful this is in general. We can probably provide some, you know, describe where we get stuck into things, but at the same time, not having prior experience in deploying the algorithm, it's kind of hard to understand if problems are because of our implementation is bad, or because maybe there's some things in the algorithm that need to be updated. So it'd be interesting to see like if other implementers also have similar issues, but I don't know how many there are.
Yeah, thank you. I think that's exactly the kind of feedback that we're looking for, of, hey, I was doing this and this was confusing, or oops, we tripped over this. Has anybody else tripped over that before? Did we hold it wrong? What happened? What's the best venue for bringing those up? Is that a GitHub issue kind of a thing? Is that a toss something in the mailing list?
I would say either one is fine. Whatever is easiest for you guys would be my take. Ian, what's your sense?
I think either is fine. So for testing, we actually created an entire like simulator just to test BBR, because we couldn't figure out any other way to test it easily. And like Cubic and Reno, which we had like trivial, like you ACK a packet, the CWIN goes up a packet, cool, we're done. You know, those tests are pretty mechanical to write. The BBR ones are not nearly as mechanical to write. And so, you know, like our simulator is open source, you're welcome to use it, although you'd have to figure out how to use it. But we can provide instructions if that's helpful. It's very quick oriented. I know Neil has packet drill tests for TCP. But I think, I mean, and I'll let Neil comment, that those are not trivial to like transport to other OSs and environments. I'm not sure. But I mean, I guess if people could tell us like what would be the most helpful, then, but probably for quick, we maybe open sourcing this, or providing documentation of the simulator would be a way forward, or maybe, I know QPAC added like kind of test suites and stuff where, you know, you kind of ran it through the test suite and made sure that like your QPAC implementation actually ended up with headers and not just garbage or crashed or something. And that was enormously helpful. Maybe, you know, we could create something of that sort. I don't know.
Yeah. I mean, if it's like the problem with simulators is usually you do a connection and then something happens, then is it good? Is it bad? So like if on top of the simulator, you would have specific like scenarios where you can say, this is actually the behavior to expect. And if that's what happens, then it's good. If not, then it's like, it doesn't need to be necessarily like a whole test framework kind of thing. It's mostly like, how do I know that my like I can run things manually and then verify that maybe like things happen, right?
Yeah.
We could probably, before the simulator, start with some things that are simpler, just to like sanity check that, like startup exit works correctly.
Yeah. The other thing is, I mean, I think being focused on Quick is good. All of the other tools are focused on TCP, and that's kind of an issue. I don't necessarily think we would implement Quick in TCP because it's already done. Sorry, we implement BBR in TCP because it's already done, but it's, yeah.
Perfect.
I assume that we will end up with many more Quick implementations than TCP implementations in the long term.
History has seemed to show that. Martin.
So regarding all this implementation advice, is the objective to just have software tools or to write like test cases in the draft? Or I guess the interim thing would be to have code somewhere and point to it in the draft. Like, will this be in the draft or is it a parallel effort?
I think it'd be reasonable if we can find a reasonable set to put in the draft. I don't think there's anything wrong with doing that because it kind of helps people get started and get up off the ground. But I think we'd want to look at what concretely we were actually doing there. Lucas.
Hey, Lucas Pardew, Cloudflare. Alessandro triggered me by talking about tooling. Yeah, it'd be great if we got more implementations of BBRv3 in Quick, but one of the tools that we have in Quick planned is QLog, which one of its primary kind of benefits and use cases back when we were doing development of Quick was around the behavior of congestion control. And so it's got capabilities and events in there where we could do things like log the congestion controller state and its changes. And we saw earlier a graph of there's a peak in this thing and it was this state update with this value. We have those events. Some of the tooling I've been working on internally has been adding just a plot of that label to an event on various charts that relate to congestion control. So it would be great if people implement BBRv3 in Quick and generate QLog events, but if they can't generate the QLog events, at least an event that's similar to within their logging framework that could be translated into one so that we could use some tooling to kind of have similarity of graphs that we're showing. Just something that came to mind.
Very nice. Yeah, thank you. Okay, thank you. I think that's really good input. So it sounds like what we're saying, if I try to summarize here, one, we want especially the working group and general community to kind of, let's go through, we've already got a list of the common scenarios we think, let's take an eye towards, okay, knowing how BBR works, what are the edge cases, what are the weird things we want to go push it on, and make kind of a set of, these are the different scenarios that we'd want to do, walk through that with our different tooling options, and potentially bring some of that into the draft if we think that would be helpful. Plus, I think there's a little bit more of, let's walk through some places that people may have tripped over in the past and see if we can kind of share some of that experience around to help other people get off the ground faster. Did I miss anything? Wonderful. All right. Thank you all. I believe that concludes our CCWG meeting this week. There is an ICCRG meeting after the break. So hopefully we'll see some familiar faces there. And with that, thank you all very much. Oh, yes. A brief PSA for Stuart Cheshire has some interesting L4S numbers that he took and was going to talk about either here or in TSVWG on Wednesday. And we said, let's group that with the other L4S work in TSVWG. So as a room full of people who care a lot about latency and getting packets across the internet, make sure you check that out on Wednesday. Thank you, Martin.